Hey folks, this is a new type of video that I am experimenting with here. It is a math book review video. I've seen many videos on YouTube doing math book reviews, and I've found a lot of them disappointing because they don't really provide much detail about the actual contents of the books in question. If you like this sort of video, let me know in the comments, and I can do more of them. I wanted to start with this book, Linear Algebra, 3rd edition by Serge Lang, published in 1987 by Springer. And before diving into the book, I wanted to just say a few words about the author, Serge Lang. He was a prolific French-American mathematician who wrote many books on many different subjects in mathematics. He was also a somewhat eccentric personality. He had a lot of strong views outside of math. Interesting guy. He studied under Emil Artin and taught at Yale. He also visited Berkeley somewhat regularly. When I was a student there, I actually met him once at a lunch event, and that was shortly before he dropped dead. So hopefully I didn't cause that, but nevertheless. It's important that you don't confuse this book with a few other books of Lang's. One of those is called Introduction to Linear Algebra. That book is intended for a first course in linear algebra, and it covers things like solving systems of linear equations, Gaussian elimination, matrix manipulation, so on and so forth. That is not this book, and that's not what this book is focused on. This book is meant for a second course in linear algebra, so it's assuming some familiarity with that more introductory material. This also shouldn't be confused with Lang's book called Undergraduate Algebra, which is an abstract algebra book. It does have a little linear algebra in it, though. And it shouldn't be confused with the Lang's book Algebra, which is a very well-known classic graduate-level algebra book, which does have a lot of linear algebra in it too, but from a much more sophisticated point of view. It's much more advanced. So let's dive into the review of the book. I'm going to start with some general comments, and then I'm going to go chapter by chapter and just give some high-level information about what's going on in each chapter, and then I'll give you my conclusion at the end. So if you're not interested in the detailed blow-by-blow, chapter-by-chapter rundown, you feel free to jump to the end of the video to get my conclusion. But starting generally, this book is focused on the basic structure theory of finite-dimensional vector spaces and inner product spaces over the real and complex numbers. There is minimal abstract algebra in this book. In particular, it's not working over arbitrary fields. It has no module theory, although the module of a vector space over a polynomial ring is implicitly used in the study of the structure of a linear operator, but he's not defining module or a ring or anything like that. There's minimal topology, although as we'll see, there is some. It's not focused on computations, and those that appear tend to be very ad hoc. So, for example, there is no Gaussian elimination in this book, and again, that's because Lang expects you're probably already familiar with that, and if not, you can read his other book. It's not focused on applications, this book, although some examples, like from geometry and from differential equations, are provided, but that's not the focus. There are problems throughout the book at the end of every chapter, and I can't really speak to what the problems are like for a first-time reader, somebody who is seeing this material for the first time. When I was reading it, this was not my first exposure. I was pretty much able to read all the problems and do them in my head, but that's not going to be the experience likely of a first-time reader. There is a solutions manual available separately by Shakarchi. You should look that up if you're interested in getting detailed worked out solutions to the problems. So let's jump into the contents of the book, starting with chapter 1. And in chapter 1, Lang presents many basic definitions like vector space, subspace, linear dependence and independence, basis, direct sum, fundamental concepts that will be used throughout the rest of the book. The key theorem that's proved in this chapter is the dimension theorem, which says that any two bases of a finite dimensional vector space have the same number of elements. And this is proved using the Steinitz exchange argument, which is a very sort of concrete algorithm, essentially, for seeing why that's true, which is a proof that I think is appropriate for a book at this level. One notable omission from this chapter, as well as the book in general, is quotient spaces are not covered in this book. And I think that's a notable omission because in a certain sense, which can be made precise, quotient spaces are dual to subspaces. And oftentimes it's more natural to work with quotient spaces rather than working with subspaces. So that does impact certain proofs later in the book. Because Lang doesn't have quotient spaces available, he has to work with projection operators to kind of make the argument work. And I think that makes it a little bit more opaque. I think quotient spaces are an important topic, and it's unfortunate that it's not in here, but that was Lang's choice, probably just because he wanted to try to keep things a little simpler. In Chapter 2, he introduces matrices. Matrices are introduced before linear maps here, and the matrix operations are introduced essentially without any motivation. In particular, there's no explanation for why matrix multiplication is defined the way it is, which uses the standard row by column convention. Again, part of this is probably because he assumes you've seen motivation for matrix operations before in an earlier course, but nevertheless, I feel that that's something that should be here, the explanation at least of matrix multiplication. He applies matrix terminology and techniques to systems of linear equations, but again, the book is not focused here on solving systems of linear equations. That's just something he's kind of showing in passing. A notable omission here in this chapter is that there are no block matrix operations. So if you're looking for that, you won't find it in this book. In chapters 3 and 4, Lang introduces linear maps. These are extremely important, fundamental objects in linear algebra. They're structure-preserving maps between vector spaces. A note of minutia here is that he uses left-hand notation for linear maps. That means you're writing the symbol for the linear map on the left of a vector when you're applying it to a vector. And there's other linear algebra books out there that write linear maps on the right. They use right-hand notation. So just keep that in mind if you're looking at his book and comparing it to other books. In terms of the matrix of a linear map, he uses the column-oriented convention for that, which is the natural choice when you're using left-hand notation. So you'll recall if you have a linear map between two vector spaces, finite dimensional vector spaces, the idea of the matrix is that you're looking at how that map acts on each vector in a basis of the source space, and you're getting the coefficients of the image vectors relative to a basis in the target space. And in this case, you're writing those coefficients vertically in columns for each image vector. So that aligns with the left-hand notation. The major result of these chapters is the rank nullity theorem, which Lang doesn't call by that name, but that's the standard name for it, which says that if you have a linear map between two finite dimensional vector spaces, the dimension of the source space is the sum of the rank of the map, which is the dimension of the image, plus the nullity, which is the dimension of the kernel. So he defines those subspaces, and he proves that theorem, and that's an extremely important result. He also covers change of basis, which shows you how the matrix of a linear map changes when you switch from one set of bases to another. Moving on to chapter 5. This is where things start getting a little bit more interesting in this book, and a little bit more complicated. So he covers scalar products, that is symmetric bilinear forms, as well as Hermitian products, that is conjugate symmetric sesquilinear forms, with a focus on the positive definite case and looking at the resulting geometry. So these are very important topics in linear algebra, and they play a large role in the remainder of the text. He covers Gram-Schmidt orthogonalization. So if you have an ordinary basis and you want to convert it to transform it into an orthonormal basis or even just an orthogonal basis, he provides the Gram-Schmidt algorithm for doing that. He touches lightly on orthogonal projection. I feel he could have said more about orthogonal projection given how important a topic it is, but it's a light coverage here. Duality is introduced via the space of linear functionals in the context of products, and he does touch upon the Riesz representation theorem, the simple version of that theorem that holds in this context. His introduction of duality via the space of linear functionals is not my favorite way to introduce duality. If you want to see what I prefer, take a look at my video on duality in linear algebra. But nevertheless, this is a fairly standard approach. He introduces the orthogonal complement and the associated decomposition and dimension theorems for that, and then applies that to systems of linear equations, as well as matrix rank, proving that the row rank of a matrix is equal to its column rank. That's an extremely important theorem in linear algebra, and seeing the proof through duality is important. More elementary books often prove that theorem using row and column operations, and it's important to see the proof using duality. It's a beautiful way to prove it, and it's a little bit more sophisticated than just doing row and column operations. He also covers bilinear and quadratic forms and their matrices, and takes a brief look at possibly degenerate scalar products, and looks at Sylvester's theorem at the end of this chapter. So there's a lot of material in this chapter, a lot of good stuff. In chapter 6, he covers determinants. Determinants are defined first in the 2x2 case, then in the 3x3 case, and then in the general n/n case. He provides a recursive or inductive definition of the determinant using essentially Laplace's cofactor expansion. And my complaint here is that he really doesn't provide any motivation or explanation as to why the definition makes any sense. It seems very mysterious, very magical. To show you this, you can see on the screen here, if you look at the bottom, this is his definition of the 3x3 determinant. And I really think that this would leave a reader feeling like they don't understand how someone ever arrived at this definition, how someone would ever think of this. And it's disappointing because it's not difficult to give a better introduction and definition of the determinant, and it's not any really more complicated or longer than this. So a little disappointed by this. He doesn't provide any geometrical interpretation of determinants in terms of oriented volume in this book, which is also a disappointment. However, you can find that in his introduction to linear algebra, the other book I mentioned before. So check that out. The determinant is shown to be multilinear, alternating, and unital in columns of a matrix or rows of a matrix, and to be uniquely determined by these properties via the Leibniz expansion. He applies determinants to problems like linear independence, to systems of linear equations, notably Cramer's rule, to matrix inverse and matrix rank. So a lot of applications of determinants are looked at here. Unfortunately, the trace of a matrix is relegated to the exercises, so you can come out of this book not knowing what the trace is or understanding its importance, which is unfortunate. Moving on to chapter 7. In chapter 7, he looks at basic properties of symmetric operators, that is, an operator that's equal to its transpose relative to a non-degenerate scalar product, with a focus on the real case. Hermitian operators, which is an operator that's equal to its adjoint relative to a positive definite Hermitian product. And unitary operators, which is an operator that preserves the product in the real and complex positive definite cases. So these are fundamental types of operators to be looking at. So that is something that is not only in this chapter, but subsequent chapters of the book. Unfortunately, I would say that there are other closely related types of operators that he doesn't cover well. Skew-symmetric and normal operators in particular are relegated to the exercises. And so that's unfortunate. The other thing I would say that's a major miss here in my mind is that he doesn't draw the analogy that exists between these operators and complex numbers. So if you look at a complex number, it induces a linear map on the complex plane through complex multiplication. And when you look at, more generally, linear operators on finite dimensional complex or real inner product spaces, you can draw a strong analogy between these operators and complex numbers. And in fact, the different sort of subclasses of operators like Hermitian and unitary and skew-symmetric and so on correspond under this analogy to different types of complex numbers. This is a really powerful analogy, and it explains or at least helps guide your intuition around a lot of results in this area, and unfortunately, he doesn't draw that analogy and make that connection. So it's unfortunate. In chapter 8, he dives into eigenvalues and eigenvectors. As a point of minutia, it's interesting to note that he allows 0, the 0 vector, to be an eigenvector. Most books do not, and the way he does that without leading to everything being an eigenvalue is that in the definition of eigenvalue, he requires there to exist a non-zero eigenvector corresponding to that eigenvalue. So it's a subtle detail, but it's something that if you're comparing this book to another book on linear algebra that you're reading, you have to be careful about because he does allow 0 to be an eigenvector. So just pay attention to that. Characteristic polynomial he defines using the determinant. The spectral theory of symmetric, Hermitian, and unitary operators and the geometrical interpretations are then provided. And I think he provides generally good coverage of these. In the case of the existence of eigenvectors for real symmetric operators, I like that he provides 2 proofs of existence, one using complex numbers. And in this proof, you're basically saying, well, a complex eigenvalue exists by the fundamental theorem of algebra, and it must be real because of symmetry. And then he provides a second proof, which uses calculus. And this proof is very interesting, and I wanted to show you that here. This proof shows that the quadratic form associated with the operator is maximized by an eigenvector on the unit sphere, where its value is just the maximum eigenvalue, and dually for minimums. So I really like that Lang included this proof, and this is a good example of one thing that I really like about Lang's writing in general, given how broad of a perspective he has as a mathematician and how much experience he has writing books in many different subjects. He doesn't hesitate to pull in, material or pull in a proof that provides insight, even if it's, introducing some material that is maybe not directly sort of in the traditional scope of the subject he's covering. So in this case, he's introducing calculus, right? But in the context of this linear algebra book. And he gives you the 2 proofs so that if you're not familiar with the material in one of them, you can read the other one. But I really like that he included this proof. And as you can see, some nice drawings here of little spheres, so you can visualize everything that's going on. I think it's a very nice proof. So moving on to chapter 9, here it's a very short chapter where he just introduces polynomials of matrices and linear maps. There's much more detail on this in chapter 11. One complaint I have is that he doesn't really provide any explanation for why this is natural to do. And I think that many students who are seeing this sort of material for the first time, when you start seeing polynomials of matrices and polynomials of linear transformations or linear maps, you question, why are we doing this? Again, who thought of this? Why does this make sense? And there is an explanation for that, but unfortunately, Lang doesn't provide it. So if you are reading this, hopefully, if you're with an instructor, they will explain that, or you'll have to search somewhere else if you're self-studying. Moving on to chapter 10, here he gets into triangulation of complex linear operators. This is proved by induction on dimension using an eigenvector and then using projection operators. And this is, again, because he doesn't have quotient spaces available, so he has to make use of projection operators. There's applications in this chapter to Markov matrices, a proof of the Cayley-Hamilton theorem, which Lang weirdly calls the Hamilton-Cayley theorem, like no one else on the planet, and an alternative proof of the spectral theorem for complex unitary operators. So some interesting stuff in that chapter. In chapter 11, he delves more deeply into polynomials and polynomials of matrices and linear operators. Here he covers the generalized eigenspace decomposition, the cyclic decomposition, and the Jordan normal form, all over the complex numbers only, though. So you're not going to see, for example, the real Jordan form. Schur's lemma is covered here. Unfortunately, the minimal polynomial is relegated to an exercise, so you can definitely come out of this book with no understanding of even what the minimal polynomial is, let alone why it's important, which is unfortunate. But again, probably just for reasons of space, Lang decided to deprioritize the minimal polynomial here. And in chapter 12, you have something very interesting and unique, and this is something. This is a chapter that really actually makes this book unique compared to other similar ones on the market. So in this chapter, Lang dives into geometric applications, and in particular convexity. So you're looking at geometric objects of different sorts. You're looking at line segments and parallelograms and so on, and then you're studying convex sets, convex holes, hyperplanes, extreme points. And he concludes the book in this chapter by proving the Krein-Milman theorem. So this is the theorem that every compact convex set in n-dimensional space is the closed convex hole of its extreme points. And I'll show you that here. This is a really interesting result to include, and it's another great example of Lang bringing in some neighboring material, right? And in this case, we're definitely making use of some topological concepts here, talking about closedness and boundedness and compactness and convexity and so on, but it's very closely allied with the linear algebra material and provides a great application of the linear algebra material. And who can resist a linear algebra book that has a drawing of an egg in it? I mean, I know I can't. So I'm really happy that Lang included this material in the book, and again, it makes this book stand out compared to others. The final material in the book is appendices, a quick appendix on the complex numbers, and then a more interesting appendix on the Iwasawa decomposition. This material is definitely, advanced relative to the rest of the content of the book. I think it would probably be better studied in the context of an abstract algebra book and class rather than this, but he crams it in the appendix here, so you can look at it if you're interested in that. And that is essentially the contents of this book in a nutshell. In terms of my kind of overall conclusion, I would say this book is pretty good for its intended purpose, but I don't think it's a great book. To me, this book doesn't provide enough motivation or intuition for important topics. And also, there's several important topics that are missing or barely touched upon at all, as I mentioned when we were going through the book. The organization of the material is also sometimes a little bit hard to follow and can make it hard to use as a reference. For example, when he's getting into his coverage of products, he's switching between the real case and the complex case and the positive definite case and the general case, and sometimes it can be difficult to remember, okay, what were our assumptions again? What context am I in? And then when you're looking up material for reference later, you have the same sort of problem. There's also some non-standard conventions and terminology, as I mentioned, but overall, it's again a pretty good book, and there also is some unique and interesting content like that chapter 12 that is studying convexity. So for that reason, it's an interesting book to look at. I wouldn't recommend it for a first exposure to this material, but I would recommend it for like a secondary or tertiary exposure, or if you want another reference relative to books that you're already looking at. As a general rule with Serge Lang, personally, I never like learning material for the first time from Lang. I find that his exposition just sometimes is rather unforgiving in terms of lack of motivation or intuition, and sometimes kind of presenting things in the most complicated way to start. Not so much in this book, but in other books of his, I've experienced that. And so I don't like learning from his book for the first time for a given subject. However, I always like to know what Lang thinks I should know about a topic. And his books, again, bring the great perspective that he had as a mathematician. And they're usually, advanced texts that require you to really know your stuff. So for that reason, I always like to look at his books on a given subject if I want to kind of see, what he expects me to know about that, what he thinks is important. So that's the book. I hope this review was helpful. I know it was a little bit long for a video. It's almost 25 minutes, but I wanted to, again, dive in a little bit deeper to the actual content of the book in doing this review. Hopefully that was helpful for some of you. If you like this sort of review, let me know in the comments. There's many other books on my bookshelf, and I'd be happy to do more of these. So that's all. Thanks for watching, and see you next time.